Okay, so now I'm going to look at limits involving exponentials where the base involves a variable and the exponent involves a variable. In this case, we're going to use something that's similar to logarithmic differentiation. Now, upon direct substitution, this limit becomes, let's see, it's going to be 1 plus 1 over infinity to the infinity power. 1 over infinity is 0, so I get 1 to the infinity power. That's an indeterminate form. We don't know what that is. We cannot determine the limit's value from that. We can't even really determine if the limit exists. So that's an indeterminate form, but it's not one of the indeterminate forms that I can handle using L'Hopital's rule. So what I'm going to do is I'm going to do something very similar to logarithmic differentiation. So here's how I'm going to start it off. I'm going to let this limit equal y. I'm going to call that limit y. It wasn't originally called y, but I'm going to call it y. And then I'm going to take the natural log of both sides of this equation. So the natural log of y is equal to the natural log of the limit as x approaches infinity of 1 plus 1 over x to the x power. Okay, now that I've done that, I know that 1 plus 1 over x to the x power is continuous everywhere except where x is equal to 0. If x is equal to 0, then I have division by 0 there. So as long as I'm not dealing with x equaling 0, this function is continuous. It's continuous everywhere in its domain, which is every number but 0. So since I know that this is a continuous function, I can apply this theorem. This theorem says if f is a continuous function, then I can interchange the natural log and the limit. You see, the natural log of the limit of f of x equals the limit of the natural log of f of x. So that means this is equal to the limit as x approaches infinity of the natural log of 1 plus 1 over x to the x power. Now, why would I want to do that? Well, now I can bring this x to the front and write this as the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. All right. And upon direct substitution here, let's see what I get. I'll get infinity times the natural log of 1 plus 1 over infinity, which is, let's see, that's infinity. And then this, because since that's 0, 1 over infinity is 0, that's just the natural log of 1, which is 0. So I get this indeterminate form, which is a little bit better than the first one I got, but still it's not one of the indeterminate forms that L'Hopital's rule deals with. So I'm going to rewrite that integral now, or that, not integral, I'm going to rewrite that limit now. I'm going to rewrite that limit so that when I plug it in, I'm going to get either infinity over infinity or 0 over 0. I know that when I plug infinity into this factor, I get 0. So I'm going to see if I can make that into something that is going to have 0 on the other part of the quotient. So let's rewrite that limit. I'm going to rewrite that limit. This is equal to the limit as x approaches infinity. And I'm going to rewrite it leaving the natural log of 1 plus 1 over x. I'm going to make that the numerator. And the denominator, well, I'm going to bring this down to the denominator by making it x to the negative 1 power. X to the negative 1 power. So I just bring x to the denominator of the fraction. Now, upon direct substitution, I get the natural log of 1 plus 1 over x divided by, not 1 over x, 1 over infinity, because I'm directly substituting in infinity. So the natural log of 1 plus 1 over infinity over infinity to the negative 1 power. Well, 1 over infinity is 0, so the natural log of 1 is 0. And infinity to the negative 1 power is 1 over infinity, which is also 0. So there I have an indeterminate form that I can use L'Hopital's rule on. So now that I know that, I'm just going to go ahead and I am going to go ahead and calculate the limit as x approaches infinity of the two derivatives, the quotient of the two derivatives. Well, the derivative of the natural log of 1 plus 1 over x is the derivative of 1 plus 1 over x over 1 plus 1 over x. The derivative of 1 plus 1 over x is, let's see, negative 1x to the negative 2 power. That's the derivative of 1 plus 1 over x. And I'm dividing that by 1 plus 1 over x. And the derivative of x to the negative 1 is negative 1x to the negative 2. So I get this, which is equal to the limit as x approaches infinity. And let's see what we have here. This will be negative 1 times x to the negative 2 power over 1 plus 1 over x multiplied by, and then I'm going to flip the bottom over and multiply by it. So it's going to be 1 over negative 1 times x to the negative 2 power. Those are going to cancel out. And I'm going to get that this is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. And upon direct substitution, that becomes just 1 over 1. 1 over 1. And there I've calculated the limit. There I've calculated the limit. Actually, I've calculated the limit of the natural log of y, not the limit of y. So what I'm going to do is I'm going to go back and say, hey, I know that the natural log of y is equal to this limit. The natural log of y is equal to this limit. Natural log of y is equal to this limit. Therefore, since the limit is equal to 1, that means the natural log of y is equal to 1. And if I want to know what y is, my original limit, this equation says that y is equal to e to the first power if you change it into an exponential. So we have y is equal to e. So this limit is equal to e. And that is how we're going to use this theorem whenever we have something where the exponential has a base that has a variable and also an exponent that is a variable.